Assalamualaikum warahmatullahi wabarakatuh. My name is ANATASHA NABILAH Binti SUHAIMI. My matric number is 2023627432.
My name is Cikgu ROSSUHAILA binti Cikgu RAMLI and my matrix number is 2023862736.
Hi, my name is Elieni Binti Mukhtar. Nombor matrik 2023857998.
For this assignment, we decided to observe the unemployment rate in Malaysia. This data was taken from the statistic portal. The objective of this study are: the first one, to solve the best fit line and curve; the second one, to distinguish the three approach to the curve fitting; and the last one, to make a prediction of future trends using the best fitting function. This figure represents the data from the website for the unemployment rate in Malaysia from 1999 to 2022. Based on the data given, we decided to make an observation on 20 data of the unemployment rate in Malaysia starting from 2003 until 2022. We determine the independent variable. X variable is the year where we let 2003 as 3, and the dependent variable Y variable is the unemployment rate. Next, we move to construct and plot. For least square line, first we need to write the linear function to be fitted, which is yx equal to a0 plus a1x. Then we write the normal equation in metric form. Since we have two variables to be found, which is a0 and a1, we use the metric 2 by 2. The normal equation in metric 2 by 2 consists of n, sum of x squared, sum of y, and sum of xy. Next, we use Excel to find the values for all the elements of the matrix. After calculating, we get the value for n equal to 20, sum of x equal to 250, sum of x squared is 3790, sum of y is 68.62, and sum of xy equal to 869.48. Next step, we can find a0 and a1. We use regression mode by substitute all the value that we get earlier in the standard matrix. Then, by the equation mode, we can get the value for a0 equal to 3.2105 and a1 equal to 0.0176. Lastly, we substitute a0 and a1 values into the standard linear function. So, the solution equation for least square line is yx equal to 0.0176x plus 3.2105. This graph shows the distribution between year and unemployment rate. This graph also shows the best fit line between the data, where the equation of the line is y equal to 0.0176x plus 3.2105.
Next, we will construct and plot a least squares polynomial function. There are 6 steps to make the function. Step 1, we have to determine the degree, which is denoted as m. For our assignment, we choose m equal to 2. Step 2, we write the general expression of the polynomial where ys equal to a0 plus a1x and a2x squared. Step 3, we write the normal equation in the matrix form 3 by 3, which is include the values like n, the sum of x, x squared, x cubed, x power of 4, y, x multiplied with y, and the sum of x squared multiplied with y. We use this matrix equation to search for a0, a1, and a2. Then, we go to step 4 to find the values for all the elements of the matrix. This table is the calculation of x squared, x cubed, x power of 4, x multiplied with y, and x squared multiplied with y for each data. Then we get the sum of x equal to 250, the sum of y equal to 68.62, the summation of x squared is 3790, sum of x cubed is equal to 64,000, sum of x to the power of 4 is 1151386, sum of x multiplied with y is 869.48, and sum of x squared multiplied with y is 13434.14. Next, step 5. We solve for A0, A1 and A2 by regression mode. We substitute the values we get earlier into the matrix equation. Then, by equation mode, we get A0 equal to 4.1732, A1 equal to negative 0.178, and A2 equal to 0.0078. Lastly, step 6, we write the least square quadratic function by substitute the value of A0, A1 and A2 into the polynomial function. Then we get yx equal to 0.0078x squared minus 0.178x plus 4.1732. Next, this graph shows the distribution between X and Y, which is the year and unemployment rate. This graph also shows the best fit line, where the equation of the line is the one that we got just now.
Next is alternative function. So the step 1 to find the alternative function is identify the expected function. We choose exponential model as our alternative function, which is y equal to alpha exponent beta x. Step 2 is identify the unknown, which is we need to identify the alpha and also the beta. Step 3, we need to linearize the function. So we got ln y equal to ln alpha plus beta x. So next is step 4, which is transform the data. From the linearize, we can transform the data into y equal to a0 plus a1x. And we got the y is ln y, a0 equal to ln alpha, and a1 equal to beta. Step 5, we write the normal equation in metric form 2 by 2. For step 6, we need to find the value for all the elements of the matrix. So we find the value of x, x squared, y, xy, and we find all the summation of the elements. Next is step 7, which is solve a0 and also a1. By regression mode, we substitute all the elements into the metric forms 2 by 2. And by EQN mode, we got the value of a0 equal to 1.17225 and a1 equal to 0.0044. For step 8, we need to solve for the unknown, which is a0 equal to alpha exponent alpha equal to 1.17225. So we got the value of alpha equal to 3.2293, and the value of beta equal to a1 equal to 0.0044. So step 9 is the expected function. We got the function is y equal to 3.2293 exponent 0.0044x. So here is the graph for expected model, which is y equal to 3.2293 exponent 0.0044x. Next is accuracy of all approximation. Sum square error, which is SSE, is an accuracy measure where the error are squared and added. It is used to determine the accuracy of the forecasting model when the data points are similar in magnitude. the lower the SSE, the more accurate the forecast. Understanding this accuracy statistic will help to choose which forecasting model best fits to data. So the formula of SSE is the summation of y minus y bar squared.
To find the SSE for a least square line, first we need to find y bar by substitute x value into the equation for least square line that we get earlier. After that, we find the square root error by square y minus y bar. So, SSE for linear function is 2.45667940.
Next, for SSE for least square polynomial function is also the same. First, we search up for y bar and then the value of y minus with y bar. And then we get SSE for each data. Next, we sum all of the SSE and get 1.38205384 for the polynomial function.
So to find the SSE for our Binti function, we need to know the value of y, also the y bar. The value of y bar is we use the function of y equal to 3.2293 exponent 0.0044x, and we substitute the value of x into the function. So to find the SSE, we need to substitute y with the y bar and square it. So the sum square error, which is SSE for alternative function, is equal to 2.4586729196.
For the conclusion of our assignments, based on the calculation that made by my group members, the SSE values we get from three model functions, which are SSE for the linear model is 2.45667940. For the polynomial quadratic model, we get 1.38205348, and we get 2.4586729196 for the exponential model. From these three models, we decided polynomial quadratic model is the best function that fits the data because it is more accurate since its sum of square error is the lowest among others. For the future trends, we predict that the unemployment rate in Malaysia will increase. As we can see, the function in the model suit the data the best than other functions. This function that has a wide range of curvature types allows them to fit data patterns that may not be adequately captured by linear models. We made the predictions that it will increase as the quadratic model is easy to understand and has straightforward interpretations in terms of curvature and the direction of the relationship. Furthermore, although this function is simple to make predictions, it also has its own limitations. When predicting the future trends from the range of observed data, quadratic functions are less reliable predictions. This is due to the possibility that the curvature that the quadratic equation assumes could prove to be true outside of the observed range, which could produce predictions that are not accurate. In conclusion, from this dataset and three model functions, the best model is the quadratic function since it has the most fit accuracy as its SSE is lowest between linear and exponential functions. Even so, its limitation need to be underlined since the prediction may not be accurate from the range of observed data.